This is Lesson 6 in our Calculus 1 series, Continuity. A function f is said to be continuous at x equals a if the limit as x goes to a of f of x is equal to f of a. If f is not continuous at x equals a, we say f has a discontinuity at x equals a. Intuitively, continuity means that we can draw the graph of y equals f of x near x equals a without picking up our pens. For example, this graph here is of a function that is continuous at all real numbers. We can sketch this graph without lifting our pen once. This graph has a jump at x equals 1. It's continuous for all the values before x equals 1 and all the values after x equals 1. But at x equals 1, the limit as x goes to 1 of f of x does not exist. The limit from the left is not equal to the limit from the right. So that limit doesn't exist, and so certainly it can't satisfy the condition here to say that this is equal to f of a. This limit doesn't exist in that graph. Here we have a discontinuity at x equals 2, because the limit as x goes to 2 of f of x is not equal to f of 2. Now we have a two-sided limit that exists, but it's different than the function definition at x equals 2. So this graph is of a function that's not continuous at x equals 2. Similarly, this graph also has a discontinuity at x equals 2, simply because f of 2 does not exist. And I want to point out a couple of things about the definition of continuity. The first thing is that saying the limit as x approaches a of f of x is equal to f of a is equivalent to the following three statements. The first thing is that we're saying the limit as x approaches a of f of x exists, and we mean as a two-sided limit and as a real number, not infinite. We're also saying here that f of a exists. That means x equals a is in the domain of f. And the third statement is saying that those two quantities equal each other. So when we're explaining discontinuities, it's often helpful to remember these three separate statements, so we could explicitly state how the function fails to be continuous at a point. The other thing I want to point out is that f being continuous at x equals a means that we can push or pull the limit through the function. So the definition of continuity is that limit as x goes to a of f of x is equal to f of a. Well, notice that f of a is really f of the limit as x goes to a of x. Here, on the left, we're saying, look at all the f of x values as the x values approach a and take the limit of the f of x values. But here we're saying, let x approach a, then plug that limit value of a into f. And continuity means they're the same. So essentially we're able to push this limit through the function, or pull it out of the function. And that's an important property to note. It comes up a little bit in Calc 2. Let's take a look at some more definitions. If the limit as x goes to a from the right of f of x is equal to f of a, then f is said to be continuous from the right. If the limit as x goes to a from the left of f of x is equal to f of a, then f is continuous from the left. So here we have a function that is not continuous at x equals 1, but it's continuous from the left at x equals 1. Because the limit as x goes to 1 from the left is equal to f of 1, the function evaluation at that point. We have the closed circle here being the same value as the left-sided limit. Here, again, we have a function that's not continuous at x equals 1, but this one is continuous from the right at x equals 1. And that's because the limit as x goes to 1 from the right of f of x is equal to the function evaluation at that point. It's because we have the closed circle equal to the limit from the right. This graph here is of a function that's not continuous from the left or the right, because here we have the two-sided limit existing, but neither one of those left or right limits is equal to the function evaluation at that point. Let's take a look at some more definitions. If the limit as x goes to a from the left of f of x is not equal to the limit as x goes to a of the right of f of x, f has a jump discontinuity at x equals a. So here we have a jump discontinuity at x equals 1, because the limit from the left is not equal to the limit from the right. If the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, but that limit is not equal to f of a, or perhaps f of a is not defined, does not exist, then f is said to have a removable discontinuity at x equals a. So here we have the two-sided limit existing, but that limit is not equal to the function evaluation at that point. That's called a removable discontinuity, because we could get rid of the discontinuity by just redefining the function's evaluation at this one point. Similarly here, the two-sided limit exists as x goes to 2, but f of 2 is not defined. So again, we have a removable discontinuity at x equals 2. If the limit as x goes to a of f of x is positive infinity or negative infinity, or if just the left or the right limit is positive or negative infinity, then f is said to have an infinite discontinuity at x equals a. So in this graph, we have the limit as x goes to 3 from the left of f of x equaling positive infinity. It doesn't matter what's happening at x equals 3 or on the right. As soon as we see that we have a one-sided limit that's infinite, we have an infinite discontinuity. And we'll talk more about this in the next lesson when we talk about vertical asymptotes. So let's take a look at this graph that we saw in lesson 3 and now classify the discontinuities. So I'd like you to please pause the video and work on this problem. So we can see from this graph that we have 3 discontinuities here. We have to pick up our pen once at -5, again at -3, and again at 2. But let's get some more information about each of these discontinuities so that we can classify them. Here at -5 we have limit as x goes to -5 of f of x exists, but is not equal to f of -5. So that's a removable discontinuity. Here at x equals -3, we realize we have limit as x goes to -3 of f of x is infinity from both sides. So this is an infinite discontinuity. And at x equals 2, we see that the limit as x goes to 2 from the left is not equal to the limit as x goes to 2 from the right. So here we have a jump discontinuity. Now let's take a look at this definition. If f is continuous at all x values in the interval ab, f is said to be continuous on the interval ab. So let's take a look at the same graph and state the intervals on which the function is continuous. Well, we said that we have discontinuities at x equals -5, x equals -3, and x equals 2. So it's continuous on -infinity to -5, union -5 to -3, union -3 to 2, union 2 to infinity. And all of these intervals are open. Let's take a look at another. State the intervals on which f is continuous. So it's a similar type of question, but now we have a piecewise function. So I'd like you to please pause the video and work on this. Well, we see that the function definitions we have here are lines and a parabola. And we know that lines and parabolas are continuous for all real numbers. So we only need to check the x values at which the function definition changes in this piecewise function. So our only concern is whether or not the function is continuous at x equals -1 and whether or not it's continuous at x equals 2. Everywhere else, we know it's going to be continuous. So let's take a look at these limits. And to do that, because we have a piecewise function, we're going to need to look at left and right limits. So we start by taking a look at the limit of f of x as x goes to -1, and so the limit as x goes to -1 from the left of f of x is equal to the limit as x goes to -1 from the left of 7 minus 2x, because a left-sided limit is going from values less than -1, and so we're using the top function definition here. The x values are less than -1. So this is the limit as x goes to -1 from the left of 7 minus 2x, and at this point we can just plug in 7 minus 2 times -1, so this is equal to 9. And the limit as x goes to -1 from the right of f of x has x values that are all greater than -1, and so we're going to be using this function definition, x minus 2, because the x values are greater than -1. And so this is the limit as x goes to -1 from the right of x minus 2. We can just plug in here, and that's -3. We can see the left limit is not equal to the right limit, so the two-sided limit does not exist. And therefore f is not continuous at x equals -1. At x equals 2, let's see what's happening. The limit as x goes to 2 from the left of f of x has x values that are less than 2. So x values that are less than 2, we want to use x minus 2 as our function. So this is the limit as x goes to 2 from the left of x minus 2. So that's 2 minus 2, that's 0. And the limit as x goes to 2 from the right has x values that are greater than 2. So we're going to use -x squared plus 4 as the function. And so here we can just plug in, and we get -4 plus 4, that is also 0. So we see that the left and the right limits are equal. That tells us the limit as x goes to 2 of f of x exists, and it is equal to f of 2, because we do have that function definition here. That's the same value of 0. Therefore, f is continuous at x equals 2. So the only discontinuity we have is at x equals -1, and that's where we have to break up our interval. So f is continuous on -infinity to -1, union -1 to infinity. Now, based on the limit laws from lesson 4, if f and g are continuous at x equals a and c is a constant, we have that all these functions are also continuous at x equals a. So the sum or difference of continuous functions is continuous, a constant times a continuous function is continuous, and the product or quotient of continuous functions is continuous. Also, the direct substitution property we saw in lesson 4 for polynomials, rational functions, root functions, and trig functions comes from this. Here we have a theorem that says polynomials, rational functions, root functions, and trig functions are continuous at every x value in their domain. This is what allows us to use the direct substitution property when we're finding limits. We know that the limit must equal the function's evaluation at that point for polynomials, rational functions, root functions, and trig functions. So for example, let's find the intervals here on which the functions are continuous. In part A, we have f of x equals 2x squared minus 1 over x plus 3. So we have a rational function, and we know that the only x value not in the domain is the x value that's going to make the denominator equal to 0. So here we know that x cannot equal -3. And we just saw the theorem that says that rational functions are continuous at every point in their domain. So what are the intervals over which this function is continuous? They're -infinity to -3, union -3 to infinity. And here we know that for even roots, we can't have anything negative underneath. So here we need x to be greater than or equal to 0, and that's the domain. And the theorem says that a root function is continuous at all x values in its domain. So it's continuous on the interval from 0 to infinity, closed on 0. But what does it mean to be continuous at 0 when there are no x values to the left of 0 in the domain? It means that this function is continuous from the right at x equals 0. And so when we're talking about the intervals on which this function is continuous, we can include 0 with a closed bracket, understanding that it means continuous from the right at that point. Also, since continuity means we can push or pull the limit through the function, we have the following theorem. If g is continuous at a and f is continuous at g of a, then f of g of x is continuous at a. So we can talk about a composition of continuous functions being continuous. So find the intervals on which the functions are continuous. Here we have f of x is the third root of x plus 1 over x squared minus 1. So we have a composition of functions here. It's a composition of a root and a rational function, so we know it'll be continuous on its domain. Now notice it's an odd root, so we can have positives and negatives underneath it. The only thing we can't have here is a denominator of 0. So x cannot equal positive or negative 1. So the set of intervals on which the function is continuous is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. And these are open intervals. Here we have g of x equals sine of 2x to the third plus 1. We have a composition of functions. It's a composition of a trig function with a polynomial, so we know that it'll be continuous on its domain. And notice that the domain of the polynomial is all reals. And whatever comes out of that, we can certainly plug into the sine function because its domain is all reals as well. And so this domain is all reals, and so it's continuous on the interval negative infinity to infinity. Now let's take a look at this problem. Use continuity to find the limit. So here we notice we have a trig function in our denominator, and it's continuous at pi over 2. We have our numerator is continuous at pi over 2, so that quotient is continuous at pi over 2. It's being plugged into the sine function, so that's still continuous, and then the whole thing is being squared. So all of that is okay. We know that this function is continuous at x equals pi over 2. So this limit must be equal to the function evaluation at that point. And so this is going to be sine squared of pi over 2 divided by 2 sine pi over 2. So that's sine square of pi over 2 divided by 2 times sine of pi over 2 is 1, so this is 2 times 1. So this is going to be sine square of pi over 4, which remember is going to be sine of pi over 4 quantity squared. This is just shorthand notation for this. So it's going to be radical 2 over 2 quantity squared. So that's going to be 2 over 4, or 1/2. And that's our limit. Now let's take a look at the intermediate value theorem. If f is continuous on the closed interval ab, and n is any number between f of a and f of b, where f of a is not equal to f of b, then there exists a c value in the open interval ab such that f of c is equal to n. So what we're saying is that if f is continuous on the closed interval ab, here's some continuous function f on the closed interval ab, and f of a is not equal to f of b, then for any number in between f of a and f of b, there has to be a value for which the function is equal to that number, because it's a continuous function. And if the graph is going to have to get from f of a to f of b, it's going to have to cover all of the y values in between. So pick any of those y values, take any value n, there has to be a value for c in this interval for which f of c is equal to n. And the intermediate value theorem doesn't tell you how to find that value, it just says there exists that value. So how is this useful? we can use the intermediate value theorem to prove the existence of x values that solve a given equation. So here in this problem, prove that there is a solution to sine of x equals x squared minus x in the interval 1, 2. Now sine x equals x squared minus x. This isn't an equation that we can solve algebraically. But we might be interested in just knowing, is there an x value for which this is true? If there is, then maybe we'll approximate it. But we'd like to know, is there a solution here? And so this problem is saying, yes there is, prove that there is one. So we're going to use the intermediate value theorem for that. But first we need to figure out what's our f of x for the intermediate value theorem. Well, let's take f of x to be sine x minus x squared plus x. In other words, let's bring this over to one side of the equal sign. And then what we're looking for is a value for which our function is equal to 0. Because that'll say sine x is equal to x squared minus x. So we consider this function f of x, and we need to prove that there is a value c in the interval 1, 2 for which f of c is equal to 0. So let's take a look at f of 1 and f of 2 and see what we can find out about them. If we look at f of 1, that's going to be sine of 1 minus 1 squared plus 1. So this is equal to sine of 1, and remember that's 1 radian. So 1 radian is approximately pi over 3 radians. Because we know pi is approximately 3.14 radians, so 1 radian is approximately pi over 3. And we know that sine of pi over 3 is definitely a positive number, so we know that sine of 1 radian is positive. If we look at f of 2, we get sine of 2 minus 2 squared plus 2. So that's sine of 2 minus 4 plus 2. Again, this is 2 radians, so it's approximately 2 pi over 3 radians. We could think of it that way. But whatever that value is, we know that the sine value is between -1 and 1. And so if you subtract 2 from that, we're going to have a negative value here. So we've shown that f of 1 is positive, f of 2 is negative. Well, then by the intermediate value theorem, there has to be a c in the interval 1, 2 such that f of c is equal to 0. We know that 0 is between f of 2 and f of 1, therefore there has to be a c value in the interval 1, 2 for which f of c is equal to 0. And so that proves the existence of that solution. And just a note here, I tend to use math notation a lot, and this backwards capital E stands for there exists. So this says, we know there exists C in, or as an element of, the interval 1, 2, such that f of c is equal to 0. And with this, we'll conclude our lesson on continuity.